Welcome back to the hyperbolic frustration chamber. We are back once again. It is another day, another dollop of suffering, but our environment is working once again, so we have some comments available. Let us take a look. So we'll take a look. I actually didn't respond to these ones yesterday just because the environment was broken. We have a comment. I think I did pre-read this one just a little bit because it was a bit longer and I was thinking about the problem last night. But I stopped reading this one halfway through. This is just because I don't want to pretty much give myself the answer. So the way I kind of go about it, and I received this advice as well from someone much better than me, but I think the way I'm trying to go about it is I try the problem and I struggle. And then when I can't figure out another way, then I'll take the smallest amount of hint I can get, and then I'll move forward again. So I'm really trying to avoid not getting just reading the answer, because then it kind of takes away the struggle as an encoder. Because I think I think how it works, I'm thinking or brainstorming, is that you kind of have like this maze in your head, and you have to run through the maze basically to figure out the problem. And the problem is the maze. This is very meta, but the problem is the maze, and you pretty much have to work through the maze. And let's just say there's only pathways you can see through the maze based on your experience. But pretty much you end up looking through the whole maze and realize with your current pretty much parameters or your current ability, you cannot exit the maze. But to know that, I think you have to do pretty much a depth first search of the whole maze, or a breadth first search, and visit the whole maze. And then you can be like, oh, I need to look up something else to make some progress. But I want to take the smallest hint possible. That way I can find where the new edition of, the problem solving ability will go. This is all really meta to say. I pretty much try to struggle until I can't anymore, and then I try to look at something to help. But I can't say that I'm going to read the whole comment just because I think it might rob me of the satisfaction of solving it. So I started reading it, but it sounds like it could be the solution. So I stopped halfway through. This is unfortunate, but this is a necessary evil. But we do have a comment from Niall Maciek. I'm kind of stuck, bro. I keep going through the lessons on Codecademy, Free Code Camp, etc., and I don't really understand them. I'm wondering if it just has to be like this, because the first time I studied functions and for loops, it made zero sense, but now when I went back and revised, I understood why the parameter was the true, and etc. My question is, should I go through the Codecademy full stack engineer career path twice? The first time just going through it, even though I'm not necessarily getting it, then second time round I might actually understand everything. Also, I'm starting school and finishing my bachelor's in computer science, but the languages in the curriculum are PHP, MySQL, and Python, bunch of backend stuff. Should I even try learning them in advance, or just finish Codecademy and learn during the course in college? Sounds like an interesting optimization problem. Interesting. The languages in the curriculum, bunch of backend stuff. I would say, and also take my advice with a grain of salt, but with the first part of the question, I do think there's a part when you're learning where you just end up kind of going through the motions. But I think that's also important too, because I imagine it there's a lot of imagination here. But I imagine it as pretty much imagine the breadth of computer science, or the thing you're trying to learn, as like a forest. And the first time you go to the forest, it doesn't really make any sense because it's just nighttime. You can't really see anything. And the Codecademy course is like dropping a few breadcrumbs, Hansel and Gretel style, or it's like dropping a really dimly lit candle on the ground, right? Kind of like marking where you went. It's like dropping a really dimly lit candle on the ground. So it might not be usable. For example, after dropping all these small little candles in the forest, you might say, hey, I want to get to where I was originally, or something like that. You probably would still struggle to get to where you wanted to go because the candles are very dimly lit. But it's important because, maybe you might find a candle, right? And now you can kind of find another one. All this to say, I think it's kind of like dropping a little lamp post or a candle. And so it may not be usable in the moment, But in the future, when you relearn it, it'll actually be easier to figure out where you're going. So you end up going through the forest faster and actually seeing a bit more, because this is where the metaphor changes again. Hopefully the candle will turn into a fire. Hopefully the fire turns into a furnace, and eventually the whole forest will be lit, and it's very not on fire, but it'll be illuminated, and you can pretty much travel through almost as if there's nothing blocking your vision or line of sight. But it kind of sucks to say it, but I think going through it again could be useful. There's a really good document by, I think it's by this guy named Michael Nielsen. It's called if you just search into Google, Augmenting Cognition, Michael Nielsen, I think. And he talks a lot, pretty much about this idea of pretty much revisiting a piece of learning material, and pretty much how every time you revisit it, you learn a little bit more. So think about pretty much any time you learned something, when you come back, you don't really get everything that you learned, but some of it sticks, and each time you come back, a little more sticks. So you could retake the course, or I would recommend maybe try building something you're interested in. So maybe try and kind of stoking that fire, maybe building something you're interested in, taking another course. If you find that you're taking the course again and you're just like, this is kind of whack, or this is kind of not interesting, then I think you should try building something or taking another course that kind of stokes your interest. But at the end of the day, it's also part of the grind. So going through it twice, I know exactly the course you're talking about because I started going through it as well, just because I was trying to brush up on some stuff in Codecademy. And yeah, it could be useful. There could be I would think there's definitely value in going through it again. Some stuff might just drop, but I'd say there's definitely some value in going through it again. Or you can take what you learned from this course and transition it into learning stuff about what you're going to be doing in school. But I personally feel like if you're already going through the full stack course on your own time, I feel like you'll be fine in class. And it's hard to know how useful these technologies too will be. So maybe, I'm just saying, I'm kind of spewing right now, but I would say maybe try stoke your interest, maybe build something you're interested in making, so that, maybe when you are applying, that you have like something cool to show, or just kind of stoke that interest. Maybe make a game or a website or a cool app that you might think is useful. And I think that could make you go further than both of these, because you got your foothold with Codecademy and you're already learning stuff in school. Making a project could be a cool way to stoke that flame. But I don't know if it depends. I don't know about the learning in advance. If you I feel like since you went through this first part, you probably won't struggle too much in class. Which I feel like you probably won't struggle too much in class. But it's hard to know. So if you feel like you'll struggle, definitely learn in advance. But if you feel like you won't, then maybe it could be useful to do a bit of pre-learning. But that is what I would recommend. But also, you are you, so I feel like you might know best. But as I think, maybe if you tried it, just keep the flame broiling. Good things will come. But we are back once again on this problem named min cost climbing stairs. I didn't do I was going to say, keep trying to stoke that flame. And speaking of flames, something that is cooking me right now is this problem named min cost climbing stairs. So we're back again on this problem. I just finished reading the ADM for like 45 minutes. So I think we should be able to solve it this time around with Dijkstra's algorithm for finding the shortest path. I feel very intimate. I feel like I have a very intimate relationship with Dijkstra now and the algorithm itself. So maybe we can figure it out and intuit something deeper about paths and maybe the shortest paths to rewards. Feel strong, man. But maybe we'll be able to figure this out. It'll be interesting to see. That being said, I'm going to use a timer. The usual timer. It's going to be one. I don't know if we're going to do an hour because I just read for 45 minutes. We'll do 45 minutes. I'm pretty sure we're going to go over it anyway. So I just read the book, and we have quite a few differences between our algorithm. In its current form, we're stopping while v does not equal last, which is not flames, and it's also not possible to stop here because Dijkstra's works by finding all the shortest paths between S and all other vertices. If we stop when v equals last, we wouldn't have visited all the vertices, and therefore we wouldn't have found all the shortest paths between them. So if that's the case, then this case cannot be while v does not equal last. What we need to work with is while in tree, which is our array of booleans, which stores whether or not a particular vertex is in the tree, right? Which means we've seen it, right? And when I say in tree, I think it also has to do with the pretty much the shortest path spanning tree, right? So if in tree, right? Pretty much if for the current vertex it's not in the tree, then we pretty much want to put it in the tree and then visit its outgoing edges. We do that with this for loop here, right? And we're pretty much doing here is checking, right? We're pretty much, since it's going to be sort of breadth first searchy, if we angle this like how the problem is, we start at 10 and pretty much look at 15 and 20 and create the distances for them. But in Dijkstra's, we typically have to work with edges or edge-weighted graphs. Now we're kind of making it as if we're dealing with a vertex-weighted graph. So if distance sub w, which by default is set up to be infinity, is greater than distance sub v, which should be 0, or some other integer value plus the cost of w, you're going to set distance sub w equal to distance of v plus cost of w. When we start, this basically means that these indexes here, 1 and 2, are going to basically be set to 10 plus the value that was already there. So they're set to 25 and 30 respectively, which I think we see in case 1 when we print the output array. Right, but it's actually this part that actually does need some work. So I was reading in the book, and now that we've pretty much looked at our local potential paths, right? We're starting at 10, we're looking at 15 and 20. We've now, created pretty much the cost, right? The shortest path to this node right here is going from 10 to the shortest path to go to this vertex here, which would be called vertex 1, is pretty much going to be starting at 10, taking one step and going to 15, right? So the shortest, the minimum cost of that is actually 25. Same here for 30, the minimum cost to get here is 30. Right? But we need to find the next, we want to take pretty much the next shortest path. And to do that, we need to find the next node to visit. So what we did here is iterate over all of the remaining vertices, the ones that aren't in the tree, because that's important. We don't want to revisit nodes or we'd go in a loop forever. We're missing another case where we want to say and. We want to find this pretty much the smallest distance, right? And go to that next node, go to that next vertice as our starting point, right? So for example, we're adding another node here, right? To the list, which is pretty much another vertice to find. If we want to find the shortest path to this node, we start at 10, right? We looked at taking one step and two steps. We end up with these costs respectively, right? So which one of these two should we try and pretty much take to the next level? And I think that would be 25. And the reason it would be 25 is because we want to pretty much take the shortest path of all of our local paths, and it's either 25 or 30. To do that, we first have to set up a variable which we can call distance. We'll just set to infinity, and we're pretty much going to keep track of if distance is greater than the current distance to a particular node, right, then we want to take that node. We want to take that node as our next node instead, right? Also, we'd like to, oh yeah, we're going to have some shadowing if we do that. So we'll change this to dist. And we'll say dist is now going to be equal to distance sub I. So if we were to take a look at this, right, 10, 15, and 20, well, nodes, vertices 1 and 2 here are going to have a weight of 25 and 30. So we're going to say, is infinity greater than 25? Yes, so dist is going to be equal to 25, our lowest distance, right? And v is not going to be equal to I, it's going to be the next node we visit, which is this one. Then we're going to go to our next node, which is not in the tree, which is 30. I'm going to say, okay, is 25 greater than 30? No, right? Because we pretty much want the smallest distance. And so what we realized there is that we'll end up going to 25 next. So v will be equal to 1, right? And then we'll go back to the top, right? And vertex 1 is not in the tree, so we'll set it to be in the tree. We're going to visit our local nodes, right? Pretty much 30 and infinity. We're going to say if distance sub w, and distance sub w is pretty much going to be 25. Oh, no. We're going to visit our local outgoing node, so it's going to be 30 and infinity. I'm going to say if distance sub w, which is 30, is 30 greater than distance of v, which is 25, plus the cost of w. Distance of v, which is 25, cost of w would be 55. Is infinity great? Now, is 30 greater than 55? No. So we don't want to say distance sub w is going to equal this value because it wouldn't be the shortest value. So it wouldn't be the shortest distance to, it wouldn't be the shortest path to 30. So we probably know that we already have the shortest path to 30, which is going from 10 to 30. So we go to the next node, which is infinity. And then we're going to say if distance sub w, which is infinity, is it greater than distance of v, which is 25, plus the cost of w, which is actually 0. So the cost of w is from this cost array up here, and 25 plus 0. Infinity is definitely greater than 25. So we'll say the distance to this one is going to be 25. Then we're going to visit our local ones. We can either do 30 or 25, right? Both of which, the only two that aren't in the tree are going to be 30 and infinity. And we're going to take the smallest one, which is going to be 25. So we're going to be here. Going to put 0 into the tree. Visit our outgoing edges. None of them exist. So we're going to also want to add w is less than cost.length, and w is less than or equal to v plus 2. Nothing in there. We're going to iterate over all these to see whichever one is not in the tree, right? And for which distance, which is infinity, is greater than 30, right? We'll visit 30 as our last one and visit 30, but 30's next one is definitely not going to override our shortest path, so we should be done. The problem is, I think with this one, we added an extra node at the end of cost to make sure that we had one way to know the distance, the cost of the shortest path to distance. And the shortest path to distance is going to be not the value at the end of this, because the value at the end of this would be 25. The shortest path, or the minimum cost to get to this, should be 15. And that's the reason that is because you can either start at index 10 or index 25. I mean index 0 or index 1 when you can take 1 or 2 steps. We always start at index 1. So what I think that means is if we can either start at index 0 or 1, and our path, our graph, our Dijkstra always starts at 0, it means that the shortest path at cost sub, the last element in cost basically, which is going to be, if we rerun this, we should get 25. Oh no, actually, our final array, yes, perfect. So our final element in the array says 25. So I think the way to view this is we can either include 0 or not include it. Include in vertex 0 or not include it. So we want to say, we want to return the cost of cost.length. I mean, either the math.min of distance sub distance.length minus 1. So either the shortest path to the last node starting from 0, or the shortest path to the last node subtracting the value of cost sub 0. So we should be able to basically just do I think that's why I had min cost up, so we'll just say it's either the math.min of min cost or min cost minus cost sub 0. So it works for the first one, not for the last one, which we output 5 instead of 6. Actually, this is not that simple because it's unknown whether or not the min cost path included the second step. One way to fix this, we could use the parent array and check the shortest path to see which one it included. If it included the first one, if it included vertex 0, if it included vertex 0, then we can take the math min of that. That means it didn't include vertex 1 or vertex 2, depending on if it's 0 indexed or not. Another simple way to see if this works, you could abstract this whole runtime into a function, which you could run twice. We would still get n squared since we're just running this function twice. But that is a little messy. And we could just give it a cost, and it can just return the minimum. And we could give it a start index be a number. And we can change 0 to start, basically. And then we could just pretty much return math.min of Dijkstra's passing in cost with 0 or Dijkstra's passing in cost of 1. Oh, and I have to return, oh, I messed this up. I have to return, instead of returning this nonsense, we're just going to return feels strong, man. Feels strong. So this right here, this is the reason we do LeetCode. So being able to solve this problem is just a feel strong, man. I would never have been able to solve this problem 130 days ago. So being able to look back, that is pretty cool. Feels strong. I would definitely like a solution that doesn't require us running this twice. I think it requires the parent array. Otherwise, it's unknown whether the minimum cost. If the minimum cost includes the first path, if the minimum cost includes cost 0, if the minimum path includes vertex 0, the minimum path includes vertex 0, if the minimum path includes vertex 0, if the minimum path includes vertex 0, then we can use the parent array. No, if we use the parent array, then we can check whether or not the path to the minimum, the path to the top of the staircase if it contains the 0, if it contains the first vertex, if the path through contains the first vertex, then we want the minimum path, minimum cost to pretty much get to the top of the staircase. You can either use this start at the 0th step or the first step. So pretty much when we check the minimum cost of the last minimum cost to get to the top of the staircase, we need to know which one it included. If it included vertex 0, then we pretty much want to take the min of that value and subtracting min sub 0 and adding the other one. Because it's still reachable, so you can swap the index out. What if it includes vertex 2? If it includes vertex 2, then we'd like to subtract that value and add vertex 1. That's very ghetto. That is very ghetto. That is not the wave. I'm surprised that so many solutions were accepted, because this problem is very difficult. Maybe you don't have to use Dijkstra's, but I don't think we can unlearn Dijkstra's after this. So this runtime complexity would be 2n squared, which would just be n squared. I'm not exactly proud of the 2 runs of Dijkstra, but not the worst considering how this could have gone. So I was trying to see what the solution would be like. You can make 2 important observations about this problem. First, we need to find the maximum or minimum of something. Second, we have to make decisions that might look different depending on the decision we made previously. These characteristics are typical of a dynamic. You can make 2 important observations about this problem. First, we need to find the maximum or minimum of something. Second, we have to make decisions that might look different depending on decisions we made previously. In this case, we need to make decisions about either taking 1 step or 2 steps at a time. Our goal is to minimize the overall cost. If you're new to dynamic programming, question may seem more like a medium. Don't worry though, this is a great problem for getting started with dynamic programming. Generally, there are two main ways to implement a dynamic programming algorithm: top down and bottom up. You might notice that it's the exact same problem, just a smaller input. For example, finding the minimum cost to reach step 4 is like solving the original problem. Yeah, see, this makes no sense to me. So I think we're just gonna put off dynamic programming till it's completely unavoidable. But I think this is probably why the maze thing works. Visualizing this problem as a tree problem is most intuitive to my brain right now. Visualizing it as a dynamic programming problem is hard because I think there's some entropic property where I just don't feel like I need to visualize it as a dynamic Dijkstra's algorithm is dynamic programming technically, but in terms of this solution here, just does not seem like the wave. Yeah, it's interesting that Dijkstra isn't considered here, but in another way, it is a similar problem. But this was a banger problem. This was flames. So yeah, that was very, very flames. So let me see if there are other problems remain. Seems like there are new problems at the top here every day. This is an SQL problem. So look at valid palindrome. Given a string S, return true if the S, Given a string S, return true if the S can be palindrome after deleting at most one character from it. Interesting. I think we can figure this out. I think the intuitive way to solve palindromic problems is if it's the same forwards as it is backwards. I think we could implement a solution in n squared time. Where we can create a function is palindrome, which takes a string S and returns a Boolean. And pretty much what we'll do is just compare whether or not the string is the same forwards as it is backwards. But on each iteration, we'll ignore a character. And yeah, worst case, I think that would be n squared. So to do that, we would need left, which would be equal to 0, right, which would be equal to s dot length minus 1. We could say while left is left and right, we'll say const temp is equal to s sub left. And since we're saving s sub left, we're going to replace it with s sub right. Then we'll give s sub right the value of temp, left plus equal 1, right minus equal 1. Oh no, this is the replacement function. So we actually don't have to do this. We just have to iterate from both ends going down towards each other. And we'll say if s sub left, actually, are they all lowercase? We'll say if s sub left does not equal s sub right, then we'll return false. Otherwise, we'll return true. And we'll return true to start, and just to test the function, we'll call it is palindrome with ABA, and we'll call it with BBB. We'll also call it with CAT. And we should get true, true, false. So that looks okay. So maybe we'll just go ahead. And so the goal here will be to ignore a character each time. I was thinking about casting it to an array and then removing an element from the array and then running the algorithm. That would actually give us n cubed time. So to fix that, how could we ignore? You could just add in. What if we just added an ignore IDX parameter to the function? And then what we'll do is we'll just say while left equals ignore IDX, we'll do left plus equal 1. So for example, if we passed in ABA, we pass in with an ignore index 0, we'd say left is equal to ignore IDX. Let's make it ABBA. So left plus equal 1 to get 1. Now it doesn't equal ignore IDX. Problem is on the next iteration, we wouldn't do left plus equals 1. So I think we could just say if left equals ignore IDX, We just do something like this instead of a while loop. And then we'll just duplicate this for right. I think this should work, because if it equals ignore IDX, we'll just go another step further. And I think we should just do I equals 0, I is less than s dot length, I plus plus. And then we can just say if is palindrome passing an s and then passing an I, return true. Otherwise, return false. Oh, I forgot that I wrote these two here. So in case 2, we return false. So if you remove A, wait, case 2 is ABCA. If you remove A, you get false. If you remove B, you get false. If you remove C, you should get a palindrome. Oh, I think the problem is we should probably do this after. Oh no, not even more is wrong. Wait, no, this doesn't make sense to go after. Okay, let me actually think. So A and A, right? They're the same. So we don't return false. But the issue is that we should ignore this index. So we should be returning, we still return false, but it's not working out exactly. Feels like this should, it feels like these blocks should be split up just a bit. So now if this equals A and this equals A, well, so we'd pass this in, we'd say ignore index 0. So left equals ignore IDX, we do left plus 1. We could compare B and C, we'd return false. Then we do A, B, C. We do is palindrome with S except ignore index 1 now. And say, okay, neither left nor right equals 1. So we're going to compare them. They look good. Left plus equal 1, right minus 1. So then now left is equal to ignore IDX. We actually move it forward 1. So you compare it. It's incorrect. Now we're going to say I equals C, which are I equals index 2. We compare A and A. It looks good. Try to compare B and C, but it doesn't really matter that we ignore different index because we never really get there. No, wait. A, B, and C, we want to ignore index 2. A and A matches. So do left plus equals 1, we get B for left. and C for 2, left doesn't equal ignore index, but right does equal ignore index. So now B, they both equal B. So if S sub left is not equal to S sub right, return false. They're fine. So we do left plus equal 1, right minus equal 1. They both passed each other. So we return true. Something doesn't feel right about this. So it looks like n squared is not acceptable. So n squared is unacceptable. Let me make sure this is actually n squared. Iterate over the whole array, and for each element in the array, we do is palindrome iterates over the whole array basically. So we need linear time solution. A linear time solution. I think you could make this make sense if we restart linear time solution. We load everything into a map where we map the number of characters to the number of occurrences, and a palindrome is allowed at max 1 odd occurrence. So we can just check if the number of odd occurrences is less than or equal to 2, and we should be good. One place where this would fail, we have 3 odd occurrences here, but we would technically return true. Oh no, we can only return 1. So right, we'd have 3 odd occurrences here. We have 2 odd occurrences, we'd return true. So I think we could just load everything into a map. How do we want to go about checking the number of occurrences? Well, we can just create a count actually. So the count will be the number of occurrences mod 2, and if we end up with an odd number, it gets added to the count. So we're mapping a string to a number. We're just going to say for console I equals 0, I is less than s dot length. We want to get the value. If the map already has a entry for this letter, we just want to get that value. Otherwise, we'll set it to 0, and then we'll set s sub I equal to value plus 1. And we'll just print that to start. We have a equals 1, b equals 1, and c equals 1, which makes sense. Check this one, we should get a equals 2, b equals 1, c equals 1. And we get a equals 1, a equals 2, b equals 1. Then we can just have let count equals 0, and then we'll just iterate for const occurrences of map.values, and we'll do ct plus equal occurrences mod 2. Now if we have an even number of occurrences, we end up adding 0, which is fine, but if we have an odd number of occurrences, we end up adding 1. So then we just need to return if ct is less than or equal to 2. I worried about this one. Because while you can create a palindrome for this, it's not necessarily a palindrome. Actually, we could take it a step further if we kept our isPalindrome function, and we can just check which indices all right, this would at most be linear or 3n. If we kept our isPalindrome function, we'll have 2 indices. If it's greater than or equal, pretty much if CT is greater than 2, if CT is greater than 2, we would return false. And if it's less than or equal to 2, we'll take those 2 indices does not equal 0, say indices, or say keys of map.entries. Actually, this doesn't work because we don't know exactly the specific A or the specific letter that's being removed. It's actually more difficult than I thought, because you could remove, if we had 100 A's, you could remove an A from any spot. One of those spots could make it a palindrome. What if we actually, the whole thing is pretty much stuck the way it is. What if we just did the regular isPalindrome method, except we gave it a fallback where you could have a number of mistakes, and if the number of mistakes is less than a specific value, then you could remove one character, which means I'd like to return the isPalindrome. I'd like to keep the isPalindrome function again. Except we'll just take the innards. And we'll remove this ignore IDX stuff. We'll let errors equal 0. And if errors is less than a particular value, errors is less than 1, what if we say if errors is less than or equal to 1, we can change this to errors plus equal 1. Difference being here will keep the less than equal. Actually, no, that would still work. Errors is less than or equal to 1. We have one error here basically, because when left is less than right, it stops. I'm going to do something kind of ghetto, but what if I say I want to see if this is the only reason this is failing. I mean, sure there are other I'm not understanding though. If you remove what character could you remove from this to make it a palindrome? I guess the first one, you get ED. Maybe we were onto something the first time. Maybe we should just run with this. Wait. I think we had something like this. Except I think this ran out of time. I think well tomorrow we'll just try and optimize this. And we can just do a differential function instead. But this one seems to pass pretty much all of them except this time, so we will stop there.